Okay. Hello, everyone. We are very happy to have today Aristomenis Donos from Durham, who will tell us about dissipation in holographic superfluids. Please, Aristomenis, go.
Okay, so thank you very much for the invitation. It's really nice to give a talk here. So this is certainly not a new topic. People have studied holographic superfluids for quite some time now, over 10 years. And certainly dissipation is not a new interest in physics in general. I will just talk about a few results, some aspects from the point of view of dissipation in superfluids that we found with Christiana, who is in Dublin right now, and Polidoros, who is my student here at Durham, my PhD student. So the outline of my talk will be, some introduction, motivation, and generalities. I would like to not introduce holography right away. I want to say a few general things that you can, just by power of thought, conclude about symmetry breaking and the hydrodynamics, which is attached to symmetry breaking. I will also talk a little bit about pseudo-spontaneous breaking of a global U1 and what we can say from the field theory point of view or from hydrodynamics. And then after I introduce all the ingredients that I will need in hydrodynamics, transport coefficients and equations, I will then move on to holography to discuss superfluids at zero chemical potential. So everything will be at zero net charge in this talk, as far as the thermal state is concerned. I will talk about a tool that we used in holography to extract some transport coefficients by systematically developing derivative expansion, which is the symplectic current. And finally, I will talk about the results that the conclusions that we can draw from the results that we found in holography. So my motivation, I cannot motivate this enough. So often in systems which are strongly coupled, there is no quasi-particles. And so you have to resort to first principles like conserved charges or all the long-lived modes that you can find that are attached to conserved charges, or long-lived modes that are attached to symmetry breaking. Why holography? So holography in principle allows you to do microscopic computations. If you want to take a hydrodynamic limit, you can do. You don't have to, but you can certainly do it. And not only you can derive the hydrodynamics and effective field theories without any assumptions about terms that can show up in your expansion, you just derive it. You can also compute from first principles various transport coefficients that would enter in your hydrodynamic expansion. And since holography is supposed to describe microscopic theories, in principle, you can study symmetry breaking and the dynamics of symmetry breaking even by doing linear, real-time non-linear physics, even at temperatures far away from the critical temperature. Now, it also allows you to study ground states, zero temperature configurations. But of course, there is always the worry that the limit that you take in field theory to have a holographic description might not commute with a zero temperature limit that you have to take in order to study the ground states. So some conclusions can be drawn, but that's always having in mind that you might be missing something in commuting those two limits. So what is my field theory setup in general? And later it will become a conformal field theory setup. So for the time being, the conformal part is not going to be too important. So of course, I'm going to have to ask for a field theory. I like relativistic field theories with a global U1. And I would also like to have this field theory at finite temperature. Now, I also want to have a charged operator, which transforms like this, in this simple way, under this global U1. And I'm also fantasizing that there is going to be a phase transition at some critical, below some critical temperature, where this complex operator will take a non-zero VEV, and there will be a whole a whole circle worth of VEVs, actually, because you can freely rotate this order parameter with no cost in energy. Now, I'm also imagining that I can couple this field theory to external gauge fields, external sources, A mu. Now, this A mu does not satisfy any equations. It's just an external source. And I can also deform the theory by sources for the scalar operator lambda psi. So let me start with a toy model. You can think of this as something like, let's see what happens at 0 temperature, what could happen, or what effectively could happen at 0 temperature, or what could happen without taking into account dissipation at all. So I'm writing this very simple model, which we usually write in order to study the spontaneous breaking of a global U1. So psi is a complex scalar. It has a U1 symmetry in the way that I have written my action. And it's a standard textbook calculation that if m squared is negative, and lambda squared is positive, then you can find a vacuum which is preferred over the trivial vacuum psi equals 0 and which breaks the global U1 spontaneously. So in order to discover the massless mode that we will be interested in, you write your complex field in some polar decomposition, and then this theta, because it has this shift symmetry due to the global U1, you expect it to be a massless scalar, and this is indeed what it is, with a simple dispersion relation which has to be relativistic and gives you omega equals plus minus k. So the first stupid game I would like to play is what's going to happen to this if I explicitly deform the theory by something that actually breaks the global U1. So I'm introducing two additional terms, lambda and lambda star are just sources. They are fixed numbers, complex numbers. And then I'm changing my variables again. Sorry, I'm receiving messages. And so I'm changing my variables again to something which is in some polar decomposition, and I'm writing down my action again. So now you will see that there is this extra term, which of course breaks the global U1. Theta s is a fixed number, but still I want to study what happens with the vacuum. So because of this deformation, the vacuum that I had in this undeformed theory will be slightly deformed, but only slightly due to the source delta rho s. I'm not going to worry about that too much, but what is happening is that you get terms which violate the shift symmetry in theta. So if I want to study the vacuum, remember before I could just rotate the vacuum, nothing would happen, I would get the same energy, everything would be invariant. However, in this case, you see that this cosine introduces something like a mass term when I expand it around small theta. So if I do things a bit carefully, if I expand around theta naught is equal to theta s, this is one vacuum that I'm getting. I'm getting two vacuum, by the way, now. So one has a fixed theta, which is fixed by, they both have a fixed theta. One of them is aligned with the complex deformation parameter in the complex space. So the phase of the VEV has to be equal to the phase of the deformation parameter. And then the dispersion relation will acquire a mass term. And this is basically giving you just some oscillation, which is never going to stop at k equals 0 around the equilibrium theta naught equals theta s. Now the other vacuum is at theta s plus pi. It is at the antipodal of on the circle, and this is in fact an unstable vacuum. So if you expand around it, you will find that if this delta rho s is positive, then you have a tachyon in your theory, and the complex order parameter phase wants to perfectly align with the deformation phase. So what could you expect to happen if you include dissipation? Well, you will get more or less something very similar to that, but apart from the oscillations, from the never-ending oscillations of the order parameter, you will also get some damping rate, which will come like a complex part in this dispersion relation. What else do I want to tell you now that things are still very simple? So I want to also couple my scalar to some external gauge field, and I want to compute the current, which I call here J mu, and show you that the current, the x component of the current, or the spatial component of the current, can be proportional to the gauge field. Okay, even at zero frequency, just a pure gauge field, a constant gauge field, can give you a current. And this is telling you that you have a non-zero current susceptibility. You expect that you will have a non-zero charge susceptibility, but in general, for superfluids, you can take this as a definition of a superfluid. You also have a non-zero current susceptibility. This is something to keep in mind later. So if I now move on to finite temperature, what can I keep from all this? So I'm imagining that I have some generating function, which is a function of the sources, a mu, lambda, and lambda star. And I can deform the theory, and I'm imagining that I can compute this generating function for any value of the external gauge field and the complex source lambda. Now, the interesting thing to do is to take a functional derivative of this generating function, and that will give you the VEV of the current operator and the VEV of your complex scalar operator. Now, if you also assume that this thing is invariant under local gauge transformations of the external field, which shift both the gauge field and also rotate the deformation parameter, then what would be the conservation word identity is now receiving extra pieces on the right-hand side, which are proportional to the sources that break the U1 symmetry. I believe this is not the first time that people study this, but this is something we discuss in the paper. Okay, and now what is the general game that you can play as soon as you go to long wavelengths? So I have been focusing on the superfluid, but there is also the normal fluid component in the game. And what I should be doing in general is I should be considering local variations of the temperature, local and long wavelength variations of the temperature, and also of the fluid velocity, which is the dual to momentum. And then the superfluid variable, the appropriate variable, is the phase theta that you see in the order parameter O psi, in the VEV of the order parameter O psi. So if you are strong enough and you are doing a microscopic computation, you would be able to express the stress tensor and the currents in terms of fluctuations of temperature, the normal fluid velocity, and as well as the superfluid velocity. And then you would plug these equations in your conservation laws, and you would form a closed system for all the variables T, V mu, and Vs. So in total, if you are, let's say, in 4 dimensions, you have a temperature, which is 1. The fluid velocity would be 4, but it is constrained to have norm equal to -1. So this is really 3 independent components. And then you also have one scalar theta, and that gives you in total 5 quantities to be determined by the 5 equations that I'm writing over there. So that could be a closed system of equations. So in this talk, I'm going to do something much simpler. I'm not going to have to worry about the normal fluid component at all, because everything will be at 0 net charge. And the normal fluid and the superfluid component just decouple in that limit. Well, they decouple in the linearized regime. If I'm doing nonlinear hydrodynamics, everything would couple to everything. But within linearized hydrodynamics, those two things would decouple. And this is an okay thing to do, because the superfluid component is supposed to carry no heat. So anyway, I would still like to decouple currents from currents and really have a clear picture of what is the superfluid, what is the normal fluid, and working in the 0 charge limit just lets you do that with almost 0 effort and 0 complication. So in this game, then I would only need to consider fluctuations of the phase of the VEV of my order parameter, and then I would have to express the currents in terms of as a derivative expansion of the phase of my wave. Right. So this is the basic variable. And when you're doing hydrodynamics, it's good to be careful about your expansion parameter. So C here, delta C would be something of order 1, well, perturbative, but order 1 in terms of derivatives and wavelengths. And then each derivative would bring a factor of epsilon. Okay, so every derivative that I see acting on delta C would be bringing the order down by epsilon, or the order up by epsilon. So how can this expansion start? Well, when there is no space-time dependence on my phase, I know that I have a thermal state without any currents. And so when I start expanding the currents in terms of derivatives of the phase, the first non-trivial thing that I will see is just a first derivative of the phase. Okay, so the leading terms that you can write in these constitutive relations are, I mean, they seem to be universal to me. There is not too much room in terms of what you can write down. So as I have told you, the phase and the external gauge field, the phase of the wave and the external gauge field, are going to form a gauge invariant combination. And since the currents of the theory are gauge invariant quantities, then I can remember that if I have no time dependence and no space dependence, then the variation of the electric charge is going to give me the charge susceptibility. And if I start making things varying very slowly in time, I will have to make sure that I'm combining everything in a gauge invariant way. The same thing will happen with the current. I told you that there is a non-zero current susceptibility. So if I vary the X component of my gauge field, I'm going to definitely get a current, the persistent current. And as soon as I start making everything varying slowly with space, I will have to form a gauge invariant combination with a phase. So far, everything did not have an explicit, I didn't tell you much about the explicit breaking or the explicit sources that I could introduce by using the complex operator. That is the deformation parameter lambda. So if I look at the current conservation equation here, and I imagine that J is at leading order epsilon, then the derivative on the left-hand side will be order epsilon squared. So this equation is telling me that everything would still be okay if my sources in the scalar are order epsilon squared. Okay, then I wouldn't have to modify the constitutive relation for J at all. That would only introduce higher order terms. And at leading order, I can just go ahead and solve this equation by also having external sources. And by the way, it's, I think, very useful to say for people that have played this game before, that we have fixed a frame in which what you would define as the chemical potential is simply the time derivative of the phase. I can do transformations and bring in additional dissipative terms into this, but I have said that there is a microscopic origin for my phase, so I would like to keep it like this for the time being. So if I make a transformation in this, then I will have some phase and some chemical potential, but the phase that I will be talking about is not exactly this. Okay, this is just fixing a frame. It's not a big deal. So far things to me look pretty tight. There is not many different things that I can say. And so I can just go back to my word identity, plug everything in, and also tell you that I can decompose my complex scalar source into two terms. The first term will only be real, and it will be time independent. So that would be like the delta rho s that we introduced in the toy model, and which is supposed to break the symmetry pseudo-spontaneously. The delta S psi is supposed to do perturbations in the phase of the complex order parameter, And that can be a time-dependent and a space-time dependent source for your scalar operator. So if I expand everything in my word identity, this is what I have written here. I can then plug in the constitutive relations, and I can start solving. And I'm finding a dispersion relation, which is simply going to give me the speed of sound, which is something universal, the ratio of susceptibilities, plus a small mass term, which is related to this delta rho s. And since I haven't included dissipative effects in whatever I'm talking about, I can only see some oscillations. Okay, so after we include dissipation, we will see that there will be a modification of that. What else do I want to say? Something to tell you now that things are still very simple is that if I go close to the phase transition, then what I'm expecting to happen is that this chi jj will go to 0. And therefore, this speed of sound will just go to 0. And also notice what we noticed in the toy model, that if I take a negative delta rho s, I'm introducing an instability in the system. Okay, so let me start taking into account now dissipation. Now, dissipation is captured by higher derivative terms that I can write in the constitutive relations. And there is 4 different types of higher derivative terms that you can add and that can capture dissipation. However, due to the symmetries of whatever we are discussing, it is only 2 transport coefficients that are going to be relevant in this game. So the first transport coefficient is what I'm calling psi. And the second transport coefficient is what I'm calling sigma d. And I also want to register what is going to happen in normal phase fluid at 0 charge. So as I will have to take this chi jj to be 0, so that term would be gone. So this chi qq term is going to give me a term which is proportional to the variation of the chemical potential, which I am allowed to discuss in a normal fluid. This term will basically, okay, so this chi jj will go forever. And this will tell me that the time derivative is now of order epsilon squared, as opposed to the space derivative, which is still of order epsilon. So I can think of this term as being something higher order. Okay, so the leading terms would be this and that term, and I can forget completely about this term. So in that case, I will have a very simple system, which will only give me a diffusive mode. Okay, I will later talk a bit more about this mode. And sigma d is what people call the incoherent conductivity. So now, what do I want to do after introducing dissipation? Well, I want to basically solve the word identity and eliminate delta c, and write everything in terms of the sources delta s mu, not delta a mu there, sorry, and delta s psi. Then I want to express the fluctuations of the waves of the current and of the scalar operator in terms of the sources. And then I'm going to read off the retarded Green's functions by basically using this very simple relation, which is connecting the perturbation of the wave and the perturbations of sources through the retarded Green's functions. As you expect, everything is going to be determined in terms of the susceptibilities that I have at leading order, the transport coefficients psi and sigma d, and I can also write down a Kubo formula that relate low frequency limits and long wavelength limits of my Green's functions to these transport coefficients that we have introduced before. So if you can do a microscopic computation and you can compute these retarded Green's functions, then okay, you take this limit and you have extracted these transport coefficients. Now, one of the things that happens here, naively, I was expecting that something dramatic would happen with the retarded Green's function for the transport current. But if you look at the expressions that we have in the paper, and I have not included here because it's too complicated, And I think the whole point is what I'm saying here. So at k equals 0, where I want to compute the conductivities, the transport current and the phase operator completely decouple. Okay, so it doesn't matter if you have explicitly deformed the theory and broken explicitly the U1, you are still going to have a persistent current at low frequencies. So you will still see this pole. And I believe that there is some interesting work where you can include vortices or other effects so that this current can in the end relax. But this is not here in what we are discussing. Now, the other thing that I try to get at is that all the Green's functions have a pair of simple poles which are related to our pseudo-Goldstone mode. And the dispersion relation of this Goldstone mode is exactly what I'm writing here. So what you have is again the appearance of the susceptibilities, the transport coefficients, and this W here is determined in terms of the explicit deformation that breaks the global U1 very softly. And as you can see, or as I promised, apart if I take k equals 0 in this thing, and I look at what the phase wants to do as an oscillation around the phase of the explicit deformation, I will have this oscillation given by this mass term, but I will also have some damping rate, which is determined in terms of the explicit deformation parameter and transport coefficients and the susceptibility. And this has also appeared in a recent paper by Blaise, Valles, and Delacretas. Okay. Now, what can happen at the transition? Okay, so I told you that above the critical temperature there is a normal fluid, 0 charge, and below the critical temperature you have some modes or a pair of modes which have precisely this dispersion relation, and I did take the explicit deformation parameter to 0. So above the critical temperature, you have this diffusive mode, which is given by this expression. And below the critical temperature, you have a speed of sound. Sorry, this term should be linear here. There should be no k squared. It should be just k. And what will happen as I'm approaching the critical temperature is that this term will go to 0, the speed of sound goes to 0, and this term will also become purely diffusive. Well, and I have to be a little bit careful with these limits because I don't know what's going to happen with all these numbers that I have in front of me. So you have to be able to either try to guess what's going to happen in close to the critical temperature with these coefficients, or have a framework where you explicitly compute things like holography. So naively, it appears as if, I mean, if this psi goes to something finite, as I'm taking the temperature close to the critical temperature, that would all disappear altogether. But this is not going to happen, as we will see. Good. So, and I'm very much interested to see whether there is any continuity between these two modes. So as I'm taking the temperature close to the critical, this is becoming purely diffusive with some diffusion constant. Right above the critical temperature, this is the only mode that I have which is diffusive, and I want to see whether there is some continuity between them. So is there any questions at this point?
Hey, Aristos.
Hi, Blaise.
There we go. One quick question on the previous slide. I think it was the previous slide.
This one?
The one before that again.
Okay.
So here you still have this pole at omega equals 0. But that one, I would claim, goes away if you subtract off the current susceptibility.
That's right, yes.
So in a sense, you don't really have, I mean, I don't think there's truly an omega equals 0 pole here.
Well, it is the pole that you find in a superfluid.
But now you've broken your symmetry, your U1 symmetry. So why should you have a pole?
That pole, okay. that pole gets shifted in whatever couples to the Goldstone mode. What I'm saying in the first line is that the Goldstone mode completely decouples from Jx at k equals 0. If you look at this word identity, this one here, the left-hand side, if I take, if I take the k goes to 0 limit, the left-hand side is just 0, trivially. You won't have any coupling. So the conserved quantity is Jt, not Jx here.
Yeah.
The pole you're introducing is in the Jt correlator, not the Jx.
But here you're computing the conductivity of that phase.
The phase
and normally of that system, I mean. And normally when you do that, you subtract off the omega equals 0, k non-zero limit of the retarded Green's function, right?
But then you would tell me that the superfluids do not have a pole.
So in a true superfluid, you would find that this kind, I mean, this in a superfluid, the omega to 0 limit of the JJ retarded Green's function vanishes. In the presence of explicit breaking, it no longer does. And it's equal to KJJ.
That I don't understand. I'm just computing the retarded Green's function.
Yeah, but that's not what, when we compute the conductivity, that's not what we do. We don't just compute the retarded Green's function. It's the retarded Green's function minus this corresponding susceptibility, if it's non-zero.
Wait, but then, I mean, I'm just, okay, so in a superfluid, you would just get an identical result, wouldn't you?
What I'm saying is that the omega to 0 limits and the explicit source to 0 limits don't commute in GJJ.
If I take k equals 0, the explicit source just completely drops out. There is no issue with taking limits.
But within, okay.
And what I'm saying is that the Goldstone mode completely decouples in the k equals 0 limit.
All I can say is that at least within the hydro that we were computing, which I think is basically the same as what you have here, you can explicitly check that the k to 0 limit and the explicit source to 0 limit do not commute. And that this non-commutativity precisely subtracts off this I over omega term that you have in the explicit case and adds it in the spontaneous case.
Let me add that this is what we also check at finite charge density, agreeing with what Blaise says.
Which kind of makes sense, because now there's no, I mean, once you've broken the symmetry, there's nothing is conserved. It's.
But the conservation has to do with the charge, not the current.
I agree with that. Yeah.
So
okay.
I don't get what you're saying.
We can talk about it later. I can
what you
show you explicitly what I mean.
Let's maybe save this for the discussion.
Yeah.
Even for the informal discussion without recording, if you want.
Okay. Right. So, right. So now I want to move on to holography and compute basically these transport coefficients. So I want to model a superfluid transition at 0 chemical potential or 0 charge density. So in holography, it's convenient to talk about CFTs and not just field theories with global U1, and there will be some charge operator again on my omicron psi. I want to have finite temperature. And in order to induce a transition in conformal field theory without chemical potential, you would have to introduce some scale by explicitly deforming with a relevant operator that will bring a scale to the system, and then you can have a non-trivial phase transition. So some generalities, well, this is a holography group, so maybe I can say very little about these things. So the vacuum of the CFT is going to be modeled by ADS spacetime in Poincaré paths. So T and XD, you can think of them as the coordinates of the boundary field theory, and R is the holographic coordinate, which looks like an energy scale in your theory. Now I'm going to be particularly interested in deforming this theory, otherwise I won't get anything interesting from the vacuum. So I can deform the boundary metric, and that will be like deformations, metric deformations of the dual field theory. So that should tell you something about the stress tensor of the dual field theory. I can also have a gauge field in the bulk, which is going to be dual to the conserved current on the boundary theory. For the backgrounds that I'm going to consider, this gauge field is going to be trivial, but its perturbations are going to become relevant when we study, when we try to extract the hydrodynamics from this. And I'm also going to have a massive scalar, or we can have massive scalars, which, depending on the asymptotics, you can either introduce a source for them, or if they take a VEV, you can have source terms set to 0, but you can still have a non-zero VEV if they break some symmetry spontaneously, or if they take a VEV spontaneously. So after you do this, your boundary theory gets deformed, and the holographic conjecture, as you very well know, tells you that the generating function or the partition function for the CFT is equal to the partition function of the bulk theory. And if you go to the classical gravity limit, where everything is better understood, then this is simply equal to the exponential of the on-cell bulk action. And this is more like a semi-classical approximation. So you can use this as a powerful tool to extract VEVs of operators by simply taking functional derivatives of the on-cell action with respect to boundary conditions of your fields, which are actually setting the sources. So when you're trying to play this game and you want to extract the VEV from a bulk field, the following consideration is always important. So if you want to vary the bulk action with respect to bulk fields, then you vary your Lagrangian density, and this derivative with respect to the partial R derivatives of your fields is becoming very important in extracting the VEVs close to the boundary, the VEVs of the dual operators close to the boundary. And it is useful to think of this thing as something like a momentum density. Now, so when I'm doing linear response, the interesting thing is to take this variation, the variation of the Lagrangian density with respect to the radial derivative of the scalar field, and vary this thing on the perturbation. Okay, so that would give you some non-trivial information about the VEV. Now, if I take any two perturbations and I form this combination, and I take the divergence of this vector, this is equal to 0. Okay, this is known as the symplectic current density. You can think of it as, you can think of this statement as a generalization of Liouville's theorem in Hamiltonian mechanics, or you can think of it as a generalization of taking the Wronskian, if you have two known solutions, if you're solving ODEs, and just forming this thing, and then you know that you have something which remains constant, and this is the Wronskian. So this is a bit more general. It's also applicable for PDEs, and it comes purely from the fact that you found these differential equations by varying a local action. It depends on derivatives. So as you can see, the R component of this thing is very interesting for holography because it is hiding non-trivial information about the VEVs of your dual operators. So in particular, it's useful when you are trying to construct a derivative expansion or a hydro expansion. Right? So you have an R derivative and you have some T and X derivatives. The T and X derivatives will be typically much smaller than the R derivative. And you can use this divergence-free current to extract useful information about your hydrodynamic series. So how can I imagine that I'm constructing a hydrodynamic series? So let's say that you know some static perturbation of your bulk. And this can be a thermodynamic perturbation, or it can be some zero mode of a symmetry that you have in the bulk. Now, the way that you start building your hydrodynamic perturbation is just taking this thermodynamic perturbation, and then you dress it with some factor which has small T and X derivatives. And then you start building your expansion around it. You will start getting corrections in epsilon. Now, these subleading terms are the terms which are going to correct the waves. And they hide the first dissipative corrections to whatever you write from your thermodynamic perturbations. So even at this stage, this first correction is already hiding non-trivial information. So as I told you, the symplectic current takes two perturbations for you to say something useful. So the first perturbation that you're using is this static perturbation that you already know. And then you plug in as the second perturbation this hydrodynamic expansion, for which you can draw useful conclusions about this first order correction by studying this divergence-free current. So if you have a divergence-free current, it's always good to integrate in the radial direction. That will connect something that happens on the boundary with something that happens on the horizon. And if you are lucky enough to be able to say something useful about the horizon, then you have extracted non-trivial information about the boundary in an epsilon expansion. So in the model that we used to discuss the hydrodynamic expansion, we have the metric, we have a gauge field, which is going to be again 0 on the background. We have some neutral operator, which is going to only be used to introduce some scale to the theory and trigger the phase transition. And we also have the charged scalar operator, the charged scalar field in the bulk, which is dual to some operator on the boundary and which will take a wave below the phase transition. So this bulk action is invariant under these local gauge transformations. And we imagine a scenario where this potential V takes this form. It has some cosmological constant with the right value so that we will get ADS of radius 1 close to the boundary. And you also have these quadratic terms in the fields, and these are the masses around this vacuum, which will set the conformal dimensions of the dual operators. So again, we are deforming our theory, and the backgrounds that we expect to get will just have this very simple form. Okay, they will have rotational invariance in the XY plane, and temperature will obviously break Poincare invariance, and you will also have some non-trivial dependence on the radial coordinate R. And the two scalar fields will only be functions of the radial direction. So what happens is that below a critical temperature, this psi, the complex scalar, becomes non-zero, and above the critical temperature, psi is just 0. Now, I'm imagining that I have a black brane horizon at R equals 0, and I can always put the horizon at R equals 0 by shifting the radial coordinate. And I'm just writing these expansions here in R just to introduce these numbers, the horizon data of my background. Now, close to the UV boundary, I will have some terms, some expansion. So this term is going to give me the constant of integration that can be used as deformation in the theory. That will be the VEV of this neutral operator, which is probably not too interesting for what I'm going to discuss. rho v is going to be the vev of the complex scalar operator, and we always want to set rho s equals to 0 as long as we're discussing spontaneous symmetry break. Okay, so in the broken phase, as long as psi is non-trivial, it is good to decompose the complex field in some polar decomposition. And then this angle theta will combine with the gauge field, A mu, to something which is gauge invariant, and it will give me a new massive vector field in the bulk. This is a very well-known mechanism because the symmetry is gauged in the bulk. I will not have some global mode in the bulk, but I will get a massive vector from the bulk point of view. So the Goldstone mode is then packaged in this vector field, which is in a gauge invariant way. And if I study this vector field very close to the boundary, I will find various constants of integration. Okay, so the leading constant is just a source for the phase of the complex scalar. The constant term will be a gauge invariant combination of the phase and the source of the vector. And the subleading term is going to give me the currents. And if you count constraints and number of equations, you see that you have enough constants of integration in the end to find a unique solution. So how am I going to start building this perturbation, this hydrodynamic perturbation? So at zero frequency, I need to find zero frequency and infinite wavelength. I need to find some solutions for this BA. Okay, so what I know is from the thermodynamics is that if I vary the AT component of the gauge field on the boundary, this is like varying the chemical potential, and I know that I can build some perturbation in the bulk, which will asymptote to the chemical potential, and then the current will simply be the charge susceptibility. Similarly, for the X component, if I set the gauge field to some constant X, some constant AX, I will get a current, and in the subleading term, I will get the corresponding current, response current, and therefore I will discover the current susceptibility. So, and close to the horizon, these perturbations are going to give me some constants, which are horizon data, AX naught, and AT naught. So this is part of the thermodynamics of my background. So at leading order, then the corresponding currents are unsurprisingly being given by these universal expressions. And if I go to subleading order, I'm again rediscovering what I had written from in these more general slides, but with some very specific values for the coefficients xi and sigma d. Now, sigma d had been calculated before. I believe it is in one of the papers by Blaise. It is given by the horizon value of this Lagrangian constant, of this constant that appears in my Lagrangian tau, and also the near horizon limit of the perturbation of my gauge field that has to do with the supercurrent. Now, xi can also be determined in terms of horizon data, but this time it is something that looks different. So why is this a useful thing to do? Well, as soon as you have these expressions, you can start studying them in different regimes. So one of the regimes that I discussed earlier is what happens close to the phase transition. Now, if you look at this number xi, it explicitly depends on the horizon value of my complex scalar rho naught. So rho naught undergoes a second order phase transition, and the expectation is that it will go like the square root of Tc minus T, where Tc is the critical temperature. So the square of that will go like 1 over Tc minus T. So xi does blow up close to the phase transition. On the other hand, you don't have to look at holography. I mean, but you can convince yourself that chi jj will go linearly with the difference between the critical temperature and the temperature of the system. So at the end of the day, the product psi times chi remains finite as I'm taking the temperature close to the critical temperature. So this expansion that I wrote here seems to start breaking down because psi blows up. So if you have one transport coefficient becoming huge, this might be a warning signal that if you carry on expanding, that you will find some series that might not converge. And I think this is an interesting question. However, if you look at this mode and you take into account the fact that psi times chi remains finite, you will find that the mode itself, or the dispersion relation, it doesn't care at all about what's happening with that infinity. So the mode or the dispersion relation seems to be well behaved. And this is something that we also use numerics to check. And it doesn't look like there is something so dramatic happening with the conversion of this mode, but I think it is worth looking at this in more detail. So if we plug in everything and we keep track of our various modes above the critical temperature and below the critical temperature, we see indeed that in the normal fluid component, as I'm taking the temperature close to the critical one, I have just this diffusive mode. And right below the critical temperature, I'm getting again a diffusive mode, which has a different diffusion constant. But now, as I'm even lowering the temperature even more, but yes, so it has a different diffusion constant. And if I lower the temperature even more, this diffusion mode, or this pair of diffusion modes, will become just sound modes. And this is also that has been studied, that has been observed in a more complicated setup at finite chemical potential. So I think I have reached the end of my talk. So I hope that you're semi-convinced that holography is very powerful in extracting transport coefficients. You can do very powerful computations with it. I think it's worth to understand a bit more, the hydral convergence close to the phase transition. Of course, everything revolves around this angular mode, which is becoming meaningless as you approach the critical temperature. I mean, this phase loses its meaning if you take the order parameter to 0. But I still think it is an interesting question. Something else we are thinking of doing is to study inhomogeneous superfluids, especially since we seem to have understood something about powerful technique. It is worth examining inhomogeneous superfluids. Another story that one might want to explore is finite chemical potential. And since we have these explicit expressions and we know how the near horizon data can behave close to 0 temperature ground states, we can study dissipation as we take low temperatures in different ground states that show up in different theories. So that's all I wanted to tell you. Thank you.
Thanks, Aristos. Very nice talk. So now we have time for questions. Let's see who asks first. Remember, you just unmute yourself and ask. I see Martin.
Yeah, so thanks for this very nice talk. So I've got a question regarding what you said about this frame choice. So that this is kind of natural from your perspective from hydrodynamics, saying basically that I think DTC is precisely the chemical potential. But on the other hand side, you also find poles in the upper half plane in your retarded Green's function. So could this be related? That basically this is, even though it's a natural frame choice, it's a bad frame choice, as this was also the case for the usual Eckert or Landau frame choices. If you look at R-causal behavior?
I think that the existence of, if they are real poles, they are independent of the choice of frame. And the pole that I talked about before is, having to do with the explicit deformation parameter not being aligned with the VEV that you already have in the system. And so if you have your VEV on the real axis and you have a deformation parameter which is on the real axis but pointing in the other direction, then your VEV will want to align with your deformation parameter. And so that will definitely give you an instability, which all that it will do is to just align the deformation parameter with your VEV. So I think this is a real effect, and I don't think it has to do with the frame choice.
I think Martin got froze. I know.
That was a safe transition.
I thought we had lost you. Sorry, Martin. You were thinking.
Martin, did you hear what I said?
Yes, I heard what you said. Yeah.
Okay. I hope I answered your question.
I can also add that you would find also a pole even in the purely spontaneous case with this frame choice. But that pole it's in the upper half plane, but it's not gapless. It's not part of your hydro description. You should just integrate it out. It's not a physical pole. And its location would change depending on your choice of frame. So as Aristos was saying, it doesn't carry any meaningful physical information.
No, but Aristos was saying basically the opposite. He was saying this is physical. So I know, of course, also in your paper, in this EFT framework, you had this pole where you say, okay, this is beyond the scale where we should apply EFT, and so that's neglected. But if I got it right, the answer, then you're saying this is physical. This is just basically the anti-alignment of the source in the VEV.
Yeah.
Okay, then maybe we're talking about different things.
I think we are.
And I'm in the middle. I'm saying this is because of a bad frame choice.
Well, I mean, you can also do numerics in holography, and there is no room for choices, I guess, and you can find that there is indeed a tachyon if you introduce the wrong phase.
Yeah, so you should see that if you take the VEV anti-align with the source, you find a pole in the upper half plane in holography, not in.
But okay, Daniel, we don't find any poles in the upper half.
No, but we didn't anti-align the VEV and source.
Yeah, you should not anti-align it.
Yeah, but I think if I understood Aristos right, he says that if you do that, then it's when you find this pole. No, maybe. Did you say that? Or no?
Yes, I said that if you anti-align, you will find a pole.
Maybe. I don't know if Martin is convinced or he wants to ask. You said you had two questions in any case. So.
Oh, okay. I think I forgot the second question. Someone else can go ahead.
Okay. If he comes back, you ask again.
Yes.
So more questions? If no, I think I also had one. Yes. So I had one question when you had this plot with them. I got a bit lost with when you were talking about the diffusive mode and comparing it to the mode that gets gapped. Can you show this plot again? I think I got lost across the phase transition. Because I would. Okay, maybe. If
am I still sharing? Am I still sharing?
No. But you should be able to share. I didn't revoke your privilege.
Let me see. Okay.
It was almost at the end.
Almost at the end.
Yeah. Yeah, around here.
This one, yes, okay.
So you said that above TC, you have a diffusive mode that is charge diffusion, right? This is the one you're talking about.
That's, yeah, normal phase uncharged fluid. Yes.
But when you go below TC, even if you break this thing explicitly, this mode will still be there and will be, I think, purely imaginary, but deep down in the complex plane, right?
Right. I think I agree with you. This is for the undeformed theory.
But even if you, so yeah, this is my question. These other two modes that you plot here that get a real and imaginary non-zero gap or whatever, they connect continuously to the mode associated to the fluctuations of the scalar, of the complex scalar, right?
So yes, this.
So the other mode, my question is, the other mode that I would call connected to charge diffusion would still be there on top of the, I mean, apart from these two modes. I wouldn't, right? Like probably if you are well below TC, it will be down in the imaginary plane.
Wait,
and be purely imaginary.
You also want the third mode here?
I think so my question is, you were saying that that mode is not there, or did I get it wrong?
That mode is not there, for sure.
So you are saying that that mode becomes this, collides with another one and becomes these two modes?
So what I'm saying is that the two modes that you have below TC, as I'm taking the temperature close to the critical, just become diffusive. You can think one mode on top of the other, right below TC, because the speed of sound goes to 0.
Yes.
Okay. And then immediately after you go above TC, you only have just one diffusive mode in the normal phase.
Okay. Yeah, I think.
But it happens discontinuously in the diffusion constant. I think you also saw that in one of your papers, no? You have a discontinuity at some point. Well, this is the discontinuity.
There was some confusion with that discontinuity, but I think our last statement is that the mode, and Martin can correct me, the mode that I would call connect used to be called pseudo-charge diffusion or whatever, it will still be gapped and down in the imaginary plane with a gap proportional to the condensate. But I don't want to say wrong.
I think Christiana is in the audience. She has done quite a bit of Christiana, if you hear me. I think she has and Polydoros. They have really looked for another mode.
Okay, I'll also check and maybe.
And I'm also looking at the charge density. You know, just gauge field, no normal fluid there or nothing complicated.
Yeah. But that's the same we did with Martin.
Yes, but I think he is referring to your paper with Carl and.
Yeah, but now I'm referring to my paper with you.
Yes, I think you're both referring to two different papers.
Well, but the question is clear. I'm almost sure, that there is a mode. The mode that I would call pseudo-diffusive keeps there's an purely imaginary gap mode with only imaginary gap down in the complex plane when you are well below TC, on top of these two other modes that are continuously connected to the scalar modes that come in the normal phase.
If it is a hydrodynamic mode, Daniel, when you take K to 0, it has to go to the origin. It cannot be down.
No, but but it's not hydrodynamic. Once you're in the block,
There is infinitely many modes.
No, but this mode becomes hydrodynamic when you go to TC. This is the old story in first paper, like by Karl and Kaminsky. And at TC, you have three modes at the origin.
That's a different mode. That's a mode that has to do with the amplitude of the order parameter, and it completely decouples from this system.
Okay.
If you are at finite chemical potential, all these things couple with each other. If you are at 0 chemical potential, the phase mode and the amplitude mode just don't talk to each other.
That I agree. Yeah. Okay. Let's move on. I will think about it. Martin has his hand raised. I don't know if it means he has questions.
Yes, I can. So my question was about this Xi. You showed a Cooper formula for this Xi.
Right.
And it was a very unusual Cooper formula because usually we distinguish between say, thermodynamic coefficients and hydrodynamic coefficients. Thermodynamic one being purely at zero frequency, while hydrodynamic ones are usually purely at zero momentum. But of course, there could be also exceptions to that. So now, since if there would be not a like 1 divided by omega in this Cooper formula for psi, I would say it's a thermodynamic one. But now, because of this 1 over omega, so how should I interpret this psi from a hydrodynamic point of view? Is it so? What is it?
I think, well, it certainly has to do with the imaginary part of the Green's function, which is the dissipative part. I mean, even from the point of view of the linear response. I have to agree that the funny thing is that first you have to take the omega goes to 0 limit, and then you have to take the k goes to 0 limit. But even at non-zero k, you can still talk about the dissipation of energy, which is given by the imaginary part of the Green's function. So I would still like to call that a dissipative contribution.
Okay, I see.
Okay. Any more questions? Let's see if it's give some more seconds for official questions, and then I will stop the recording and see if there was some shy question or something that wants to be said off the record. More questions? Okay, then let's thank Aristos again for this very nice talk.
Thank you, guys.
And me
Thanks.
stop the recording.
It was fun.